In my last video, we discussed how you could rearrange or count the number of ways that you could possibly rearrange n objects at a time. We refer to this as a permutation, okay? So here's the deal. When we talk about permutations, we're talking about a rearrangement of something. And so order matters, okay? And we often refer to our permutations with this formula right here where we say if I had n total objects, okay, so we say n is the total number of objects, then we say the permutations would just be n factorial, but over n minus r factorial. What we're going to be looking at in this video is not a departure from permutations, but really kind of an extension of it. And up until now, we've been finding permutations of what we call distinct objects, things that I can tell them apart. So for instance, if I said A, B, C, D, and E, you know, how many ways exist to rearrange these? Well, you notice that these are all the same letters. So I say, well, how many letters are there? You know, I mean, there could be 5 that go in the first spot, then 4 letters could go in the next spot, and then 3 letters to choose from for the next one, and then 2, and then 1. Essentially, we said if you wanted to rearrange, you know, n distinct things, if you had n objects, and you wanted to rearrange all n objects, then we would say that there are n factorial permutations total. Okay. So here's the deal. In this video, we're going to be talking about what if there was another letter E in here? Like, how would we have treated this situation? Would we still say 6 factorial? And the hard part about this is the fact that if you were to take these two E's and switch their order around, you know, if they were not different colors, check this out, if they were both red, and I said, look, I switched those two E's around, you would not be able to tell. So we say that these two rearrangements are not distinct. They are not unique. I can't tell them apart. So the example I'm going to use now is this one here. We say, well, for instance, how many ways exist to rearrange the letters in the word mom? Well, here's the thing I want to point out here. There are 3 letters in the word mom. So typically we would just say that there are 3 factorial ways to do it. And how I'm getting this is I'm saying, well, there are 3 letters to choose from to go in the first spot. But once I've chosen an M, an O, or an M, then I have 2 left for here and 1 left for here. So one would think that there are 6 total ways in which we could rearrange the letters of the word mom. And as a matter of fact, when I make the M and this M here different colors, you could see that clearly there are 6 different ways to do it, because this MOM here is different from this MOM here in that now the green one's coming first in this second mom, and the red one's coming last, whereas it's flipped in this one. So here MMO and MMO, those are different, and OMM and OMM, those are different. But let's assume this. What if we were to say that we weren't doing this in color, that is MOM? Could I say that MOM and then MMO and MMO and OMM and OMM are distinctly different from the originals? And what I could tell you is actually there are only 3 ways to rearrange the letters in this word, because these were just repeaters. So here's going to be the idea in this video, where I'm going to ask you to rearrange the elements of something, but I'm going to throw in non-distinct terms. I'm going to throw in things that repeat. Okay, and so what we're going to have to do is we're going to have to modify this. So now with the example of mom, really quickly here, you notice that I took the total number that I got here, 6 in the first place, and it got cut in half. Like, why did this happen? The reason why is this. It says, in this case, the number of permutations is 3 factorial divided by 2 factorial. In other words, 6 divided by 2, which is 3, and I'll tell you exactly where I got this 2 factorial from. I know that if I were to have the letters M and M, how many ways exist to rearrange these 2 letters here, and I know that there are 2 factorial ways to do it. So when we took 3 factorial, what we're saying is this. We're rearrange all 3 letters. And then what we're doing is this. We're dividing by 2, so we'd say divide out repeaters. Okay. So since I had 2 M's, I divided by 2 factorial. In general, what we say is this: the number of distinguishable permutations, the ones I can tell apart, of n objects, where one object is repeated Q1 times, another one's repeated Q2 times, and so on and so forth. We basically say that to rearrange it, it's just n factorial. But what we're doing is we're dividing this by Q1 factorial, Q2 factorial, all these up to QK factorial maybe. But what these Q1, Q2, and QK represent is how many times that these repeated. You know, an object repeated, you know, say Q1 times. We would just put that number down here. So I'll put this into practice for you. I'll let you see what it is that I'm talking about here. But in the case down here, it says find the number of distinguishable permutations of the letters of Ohio. So I notice that there are 4 letters in Ohio, and any other day of the week I would just tell you that there are 4 factorial ways to do it. It's 24. But what I can tell you is that this won't work, because when you rearrange this O and this O, we wouldn't be able to tell the difference between those. So there are actually fewer rearrangements than possible. So here's how this works with this little ditty right here. We basically say, well, how many total objects are there? We say that there are 4 objects. And then what we're going to do is we're going to divide out the repeaters. So when I talk about these objects right here, did any repeat? Well, the letter O repeated, and I say, well, how many times did it repeat? You know, we said Q1 times, we would put that number here. Well, I say O repeated twice, so I'm going to put a 2 factorial here. And now the fun thing about this is H and I each happened once. I could say, well, H happened once and I happened once. Essentially, if you were to say 2 plus 1 plus 1, we would add up all 4 of our letters that we have here. Now, it is not necessary to write those ones. You only need to write in Q factorials down in the basement for anything that repeats. So in this case, we get 4 times 3 times 2 factorial over 2 factorial, where the 2 factorials kick out and we get 12 left over. So there are 12 ways to rearrange the letters in this word Ohio, and not 24. But that's because half of them you switched the O's around and you couldn't tell the difference on, so we had to cut them out. So again, find the number of distinguishable permutations of the letters in the word Mississippi. Well, I'll tell you what, Mississippi has 11 total letters in it, so our N is 11. So we would say that this is certainly 11 factorial over, now we're going to start dividing out repeaters. So I notice that M happens once, I don't worry about it. I happened 4 times, so we say 4 factorial down here. Times now, I notice that S repeats 1, 2, 3, 4 times. So we say this is 4 factorial. And then we say times now, I notice that P happens twice, okay? So we have P happening twice. So when we simplify this, I'll tell you what, 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. This one's not very fun to simplify because we have to make it, you know, go all the way down to 4 factorial on the top. But the good news is this. We're about to simplify this down. And some things I know are these, like the 4 factorial here and this 4 factorial are gone. We do need to write out what is actually in the basement. So this is 4 times 3 times 2 times 2. And you'll notice that I didn't write 4 times 3 times 2 times 1. I don't think it's necessary. But let's go ahead and divide out factors. And my suggestion is always this. If you have you know, factors down here that go into anything up here, try to place it off or to pass it off into things that are bigger. So like 2 goes into 8 and 2 goes into 6, but you know, 2 goes into 10 and it leaves behind a 5 right here. Okay, so this 2 would go into this 8 and leave behind a 4. Okay, I notice that this 4 and this 4, I can actually cancel those 4s out and this would become a 1. And then my 3, I suppose 3 would go into 9 3 times. So I'm going to circle all of the stuff we have left over. This is a good suggestion. Circle the things you have left over because we got everything in the basement to cancel out except for this 11, this 5, this 3, this 1, this 7, this 6, and this 5. So when we multiply all this out here, we could say that it's 11 times 5, this 5 here, times 3, times 1, times 7, times 6, times 5. And what we get is this, 34650. So we get 34,650 ways in which we could permute the letters of this distinguishably. Okay, cheers.